Alguém consegue confirmar se o som está bom, se o áudio está bom? Basicamente, não sei se já está alguém aqui na sessão do Zoom, deixa eu ver se está. Está bom? Ok. Obrigado. Mais um bocadinho, já começamos. Ok, então bom dia a todos. Vamos começar com esta aula, acho que é a terceira de elementos de automação industrial. Nós hoje vamos falar da parte teórica de mapas de carbono, que está aqui. We are going to discuss cardinal maps, and those are an alternative to the Boolean algebra that we've learned last week. So if you were able to do some of the examples that or exercises that I proposed last week for the Boolean algebra, that's great. And if you have some questions, we can discuss them later. But if you did those exercises, you should have noticed that though Boolean algebra is not straightforward. Sometimes it works, sometimes it doesn't. You have to go to the right instead of to the left, and this is something which makes me not really like Boolean algebra, because there is no rule which we can use to always get to the same result. We have to try. sometimes just randomly. And kernel maps are a solution to that problem of figuring out the logical function starting from a table of truth. Okay. Wait, I will use this so I can present better. Okay. Now. Okay. Agora aqui tem que pôr este. Okay, so kernel maps, how do they work? Basically, what we have to do is to use the table of truth. So we start from the table of truth, that place where we would have columns for the input variables and another column for the output variable, and we would list for all the possibilities of the states of the input variables, we would list the result that we would want to have. So this is the table of truth. If you don't remember now, you do. The table of truth for two input variables x, y, and the output f. And the goal, what kernel helps is to build a graphical representation like this, the table, which will help us get to the function, logical function, in a straightforward fashion. These tables that are built will depend on the number of input variables that you have. So if you have a single input variable, it's going to be a vector. If you have two input variables A and B, it's going to be a 2 by 2 matrix. If you have three input variables, it's going to be a 2 by 4 matrix. And when you have four input variables, it's going to be a 4 by 4 table, okay? So how do you fill the kernel map? What we put in the cells of that table, of those kernel map tables, are the min terms. You remember that we used the sum of products, which were the min terms, as a way to obtain the canonical, that means the non-simplified logical function. And what we are going to put here are the min terms. For example, in this case, we would have these three min terms, 1, 2, and 3, not the 0. And therefore, we would have to put the expression for 1, 2, and 3. And if you take a look at this, you will see that the expression for min term 1, which would be this, no, I think this is swapped. Yeah, no, okay, I will not use this example because this is, it may be not correct. Because this is 1. Okay, so this is not, yeah, this is for 0. So this is min term 0, I don't care. Min term 1, which is this one here, you can see that min term 1 is when we have x 0, so x is negative, so I will put x negative, times, because this is a sum of products, so we are going to do a product, times when y is 1. So that min term there is going to be represented by not x, y. If we talk about min term 2, that's when x is positive because of this, and when y is negative because of this. So it's going to be x, not y, okay? And then so on and so forth. I don't think this is correct because the order here is not correct. So next, I will show you a better example. So for example, let's do an algebraic simplification of this function here. Not x, y, x, not y, x, y. So what we did here was to duplicate x, y, so that we could have this and this together. Then on the left-hand side, we are going to put the y in in evidence, I think. And on the other side, we are going to put the x. So in the end, you get the result x plus y, okay? This one is easy. I think if you tried some exercise at home, and so last week you wouldn't have a problem doing this. So the problem with this is that this is easy, but as I told you before, algebraic simplification using the Boolean algebra is not, it's difficult to automate because it's not always the same way that you can find a way to simplify. When we use the Carnot maps, we have a visual and straightforward way to do this kind of simplification. So the output of a Carnot map is not going to be the canonical function as it was here. So from here, we were able to get the canonical function x not y plus xy plus not xy, okay? But we can also, from the Carnot map, find out a way to get the simplified version of the function, okay? That's something we could only achieve by doing the Boolean algebra simplifications. So how does it work? We have to identify neighboring products. In this case, we have to group the elements that we have in pairs or in groups of either 1 or 2 or 4 or 8, okay? So it's supposed to be 2 to the power of n, where n is bigger or equal to 0. So if this is 2 to the power of 0, that's 1, and that means you can do a group of 1. If it's 2 to the power of 1, that's 2, that means you can do a group of 2, like the example green and blue that we have here. If it's 2 to the power of 2, that means we can do a group of 4 and so on and so forth. So we have to do groups of groups of 1, 2, 4, or 8 elements. And these groups will then help us achieve a simplified version of the function. For example, in this case, we did the group blue group. So I'm going to draw this in blue. The blue group there, you can see that is where we have the value of y to be 1. So in this group, y is 1, so I'm going to put y. And then with respect to x, x can be 0 or 1. So if you want, you could say x can be 0 or x can be 1. But this is the same as saying, because you know that not x plus x equals 1. So this results in y. So for that blue group, basically, you just have to write y. And this is already a simplified version of the canonical function, right? And then you do the same for the green group. And it's the same, but in the other direction. So for this group, you know that x must be positive. And you know that y can be either positive or negative, therefore it does not appear. So the green group is represented just by x. These are our products. Since we are doing the product of sum, the sum of products, then we would have to sum this. So it would be y plus x, which is exactly what we found when we did the algebraic simplification, okay? What else? When we have 3 variables, we have to put either the horizontal or the vertical dimension with 4 columns or 4 rows, if you choose the second case. And there's just one thing to be careful about, which is that we are doing the identification of neighbors. So what is a neighbor? A neighbor is a state which, with regards to its neighbor, has only one change in the variable. So for example, if I do it like this, x, and then here yz, let me choose a better color. If I choose 0, 0, that means y is 0, z is 0, not y, not z. Then I'm going to, for example, put the y to 1, 1, 0. That means y is 1, z is 0. Then I would normally put 0, 1. That would mean y 0, z true. However, if I put this, these two are not neighbors. And why is that? Because from one to the other, you have changed the value of y and you have changed the value of z. So these two are not neighbors. And if you do this, the cardinal map does not work. So you have to be careful about putting always the neighbors. And the order that you use is always like this. So instead of doing what I did here, I would go back. And on the third column, I know that I need to put a neighbor of the second column. Therefore, I'm not going to change the y. That remains 1. And I just change the z, which goes from 0 to 1. Okay. And then on the fourth column, I can now take the z to be 1 and not change it, and then change the y, which goes from 1 to 0. Okay. And this, of course, here you would have to put for the x, you would have to put 0, 1. But the order that you see there ensures that we always have neighbors. If you do not do this, then it doesn't work. Okay. And why am I telling you this? Because when we have a table of truth, I don't know if I can recover something from algebra rule, perhaps here. So when we have a table of truth, like this, remember? If you pick up these variables and this, wait, come on. Yeah, here. So if you pick up these variables here, input variables x, y, and z, and you start doing your table, that would be x, y, and z would be there. So x is easy, 0, 1. The problem is the columns, right? So we can start and we say, okay, so we have here 0, 0, 0, 0, and the value for 0, 0 is 1. Sorry, I'm doing it wrong. Again, for x0, I'm going to be working on this part. So now I'm only going to take a look at the first columns, at the first row, I'm sorry. So just this row. And I'm going to say, for y0, z0, the function is 1. Then for y0, z1, the function is 0. And then for y1, z0, the function is 0. And finally, for y1, z1, the function is 1. Okay. What's the problem here? The problem is that, and this is why I'm warning you that you should be careful about this. The problem is that if you go through the table of truth, typically it's not in the correct order that you must insert the columns with. So if you do this, again, these two will not be neighbors and the cardinal map will not work. So you have to be careful when you are reading the table of truth and transporting the intended result there. You have to be careful not to do this swap, okay? If you have some questions, please let me know. I think for most of you, these are revisions, so you shouldn't have many questions. In any case, you are free to ask. Next. Okay, so now that I've warned you about the order or the sequence that you must have in order to have neighbors, I can tell you that now. How do you find neighbors? Well, neighbors are, how do you find neighbors? How do you find those groups that we are looking for? So you find the groups whenever you have a cardinal map. It is going to be something like this, for example. 1. So, okay, 0, 1. And now here, 0, 0, 1, 0, 1, 1, 0, 1. And then from the table of truth, you can actually put values in these cells. So you can say, for example, from the table of truth, something like this. Oh, when x is 0, y and z are 0, the function is supposed to be 1. Here it's supposed to be 0. Here 1, here 1, here 0, 0, 0, 1, for example. And now the process of doing the cardinal map simplification is the process of trying to find these groups. And you know that you can have groups of either 1, 2, 4, or 8 elements. In this case, we would find, for example, this group of neighbors and this group of neighbors. Okay. So you are looking for regions which have adjacent cells, neighboring cells. Then there can be a lot of examples of how to find these neighboring cells. For example, in this case, C above, you could do something like this. So this is a neighbor, right? Then with another color, this is another neighbor. Okay. And finally, with yet another color, which can be, for example, red, this is another neighbor. So what's happening here? For the purple one, we are selecting a neighbor, which is a vertical one. Then we select for the orange one, a horizontal neighbor. And if you take a look at it, you will see that we have used this element there that I'm highlighting twice already, with the purple and with the orange. So an element can be used multiple times for a group, for multiple groups, that's what I mean. So you can use the same element for multiple groups. And then also for the red one, we've used the same element, and we've used the neighbors that go from the outer limits of the table. So this and these are neighbors, but also this with that one is a neighbor. Okay. Also, in terms of column, in terms of rows, it's the same. So the upper row is also going to be a neighbor of the bottom row, because you will find this neighbor with that one, something like this. Okay. Another example is, for example, in the bottom. By the way, I didn't tell you, but that's important. In order to select these regions, you have to select as few number of regions as possible. So your goal is to minimize the number of regions and to maximize the size of the regions. In this case, in the example, the first one that I've already solved, the solution was that I would have only 3 regions, each with 2 elements. But you want to have bigger regions if possible. That wouldn't be the case here. For example, we could say, oh wait, we have here 3 in a row. Why don't we do this region? Well, we do not do this region because we can only do regions of 1, 2, 4, or 8 elements, and this region would have 3 elements, so that cannot be done. Okay. Let's take a look at the example on the bottom left. So in the bottom left, I think we would have to do also something like this. This is 1, this is 2, 3, and 4, something like this. Okay. And also for the other, we will see several examples ahead. So here's an example. We have this Carnot map. We select these 2 blue groups, and then we just have to write the function in terms of what the groups are. So for example, for the first group, I mean this one, we would have X to be positive and Y to be negative. So take a look at that. This group here, where the blue region is always on the bottom row. That means X is always positive, so X. Then these 2 columns are where Y is always negative. So you see 0, 0, and 0, 1. That means it always starts with a 0. So Y is always negative, not Y. And then with regards to Z, if you take a look at Z, Z can either be 0 or 1. First row it's 0, second row it's 1, so it doesn't appear. So that would be our first group, which is actually written there in second. And then we can do the same for the first one. Okay. So for the first one, we would do the first one, I mean this one on the top, we would do X must be negative because it's in the upper row, not X. And then the Y is always 1. And the Z changes, so it doesn't appear. So not X, Y. And we have many other examples here. I will not go through these examples. Why? Because they are already solved. So what I will do is I will try to solve new ones in front of you. I think it's easier to understand. We also have cases where we have 4 variables. In this case, we call them wx, y, z. And in these cases, the logic is the same, but the table will be a 4x4 table, okay? Be careful because you can also have neighboring cells like this, for example, or like this. So be careful about the boundaries of the table. We will see several examples. So the synthesis of the procedure is you collect from the kernel map all the ones, that means all the places where the function, where in the table of truth, it says that that combination of input variables, the function should be true. So you are going to collect all the ones in sets of 2 to the power of n bigger or equal than 0 elements. And you are going to try to find a solution where you have the least number of groups with the largest area possible. And also one element can belong to more than one group. So for example, here, in this example here, we would do something like a very large group like this. And this is possible because this group has 8 elements. That's okay. So we are going to select this very large group. Then with another color, we can select, for example, this group here, yellow, okay? And finally, we have a third group, which could be this one. Notice, for example, if I will do this, I can do this one with this one, and then this one with this one. However, if I do this, I will have 4 groups: the red, the yellow, the green, and the blue, right? There is a better way. Why is it better? Because it gives me a smaller number of groups. If I do not do the green and blue, and instead I do an orange one, which is going to be like this, I'm going to have only 3 groups instead of 4. So this is a better solution. It will return a more simplified version of the function, okay? So then you would pick up these groups and you would compute the logical function, as I will show you in several examples ahead. Again, I'm not going to talk about this example because it's useful for you to take a look when you are studying at home, but I prefer to do one from 0 here. This is more of the same. And about kernel maps, when we have more than 4 variables, typically it becomes harder to manipulate. So when you have 5 variables, for example, what you will need to do is one table of 4x4, where one of the, let's call it the outer variable, is true, and one table of 4x4 where the variable is false. In this case, the table on the right is where E is true, and then you do the combinations for all of A, B, C, and D, and then you have another table on the left where E is false, right? So if you have 5 variables, you get 2 4x4 tables. And we can do an example of this as well, no problem. So for example, here, we have an example here. I will try to do this from scratch, okay? I think it's easier for you to understand. So we have 4 input variables, A, B, C, and D. We have the output function f, and our goal is to use the kernel maps in order to compute the simplified version of this function. So we can, to start, build our kernel map like this. So we know that this is going to be A, B, C, D. Then A would be 0, 0, 0, 1, 1, 1, 1, 0. Be careful with the neighbors, as I told you. And then on the columns, we have 0, 0, 0, 1. Yeah, 0, 1, that's what I said. 1, 1, 1, 0. Okay. Now, second step is to write down the values of each of these cells. So for example, if I take the first column is where everything is 0. So that's going to be the top leftmost cell. AB 0, 0, CD 0, 0. That's going to be a 1 there. So I know that the cell values are only going to have either the value 1 or the value 0. So I'm only going to go through the ones in the table of truth, and then everything else that I do not, all the other cells in the map that I do not write down a 1, they are going to be 0. Okay, so I can use this shortcut not to have to go through all the elements. So let's go to the second element. 0, 0 for AB, 1, 0 for CD. So 0, 0 for AB, that means we are on the top row. 1, 0 for CD, that means we are here, 1, right? Third element, 0, 1, 0, 1. So 0, 1 here, 0, 1 there. I have a 1 here. Okay. Then I don't know, the seventh element or the eighth, 0, 1, 1, 1. So 0, 1, 1, 1 is going to be here. Then this 1, 1, 1, 0, 0. So 1, 1, 0, 0 is here, 1. 1, 1, 0, 1 is here, 1. So I'm doing this one. Then the second to last is going to be 1, 1, 1, 0. 1, 1, 1, 0. And finally, the last one is going to be 1, 1, 1, 1. Okay, so this is my Carnot map, which I extracted from the table of truth. Now, what we have to do is to figure out a way to group these into regions. What do you suggest? Any ideas? What is the best solution to get the smallest number of regions with the largest possible area? Ricardo, do you have the Zoom connected? Yeah. So you can write down on top of my Zoom. You can annotate on top. Are you writing? Aí uma solução que é anotar no Zoom. Reticências. Não consegue? Se calhar está aí alguma comissão. Okay, so try to explain to me and I will do it. So first group, which one is it? Which one would you call the group? Este, qual é o este? Mas nós não estamos a ver o este. Não, nós não estamos a ver. Tem que me explicar qual. Por palavras. Okay, so first one you want to do is the row of 4. So this one. This is one group, right? Okay, so then you pick up these 4, right? And then? Okay, makes sense. Okay, I think that's it. That's the best solution. Typically, people without experience would say, instead of the green group, they would do the green group like this. They would say, oh, now for the green, I do this. Okay, what's the problem with this? This is not a better solution than the one from Ricardo, because this will give you 3 groups. This would give you three groups of size 2, that's the red, plus 4, that's the blue, plus 2, that's the green. In Ricardo's solution, we would have three groups of 2, that's the red, plus 4, that's the blue, plus 4, that's the Ricardo's alternative green, which I'm going to put in purple. Okay, so that would be the purple and that would be the green. So the solution on the Ricardo solution, the one on the bottom, is better because we have the same number of groups with bigger areas. Okay. Okay, so now let's discard the green group, of course, because the purple one replaces it. And now what do we do? So now we just have to compute the logical function by doing f equals. Now I go group by group and compute the value, the variables for each group. So for the blue group, I'm in a single row. In this row, A and B are both 1, 1. So that's the row of AB 1, 1. So this is going to be AB. Then, with regards to the columns, you can see that you will have the value of C either 0 or 1. So that one doesn't appear. And the value of D, the same, either 0 or 1. So both C and D do not appear. So blue group is just AB. Then for the red group, I'm going to have the first row is the row where A and B are 0, 0, always. So AB, not A, not B. Then the first and fourth column are where the value of D is 0 and the value of C is always changing. So C doesn't appear, D is negative. Finally, I go into the last group where I can see that the value of C is always true. C changes and D is always true because the second and third row have D equals 1 always. So that's going to be D. And then in terms of columns, I can see that the value of, sorry, that was not D, B, sorry. Makes sense now? I was talking about B. I said D, but I was talking about B. And now in terms of columns, I will know that in the second and third column, D is always 1. So I'm going to put here the D. So it's going to be the BD. So now you can see that the size of the groups, so for example, groups of size 2, as is the case of the red one, will give you a term of 3 literals. Literal meaning variables. So 3 literals for groups of size 2. So groups of 2, size 2, 3 literals. Now, if I have the size 4, as is the case of the blue and the magenta group, so the size 4 will give you 2 literals. Then, if you have the size, just a moment, if you have the size 1, you will have 4 literals. This case doesn't appear here. And if you have the size 8, you will have only 1 literal. These are valid just for 4x4 Carnot maps, so Carnot maps for 4 variables. Okay. So you can see that that's why we want bigger groups, because the bigger the groups, the smaller the variables that will appear in the function, the logical function. So if my group is of size 1, I have 4 variables. That's a complex function. If it's of size 8, I have a single variable, much less complex function. Okay, that's why we want the groups as bigger, the bigger the better. So now you have this explanation here. You can take a look and see that this is not the same. So this kernel map is not the same as this, which is strange because we started from the same table of truth. And that's because the order by which you put these elements here is arbitrary. You can put any order that you would like, and as long as you are consistent, the result should be the same. Okay, so in this case, the solution used AB on the columns and CD on the rows. I used different. I used AB for the rows. That's why the table of truth is different. But in the end, actually, well, now I don't have the function anymore. But in the end, the function that we get should be the same that we had obtained in previously. Okay, continuing. Now there is a connection between. Let me just see. Yeah, right. So now we are going to talk about. There is a problem. Strange. Yeah, it cutted the title, this presentation. And just to make sure that I'm not saying something wrong, this is an X decoder for 4 segments. So what are we looking at here? We are looking at a way to transform 4 input variables, which are B1, B0, B1, B2, B3. These are 4 input variables, so logical variables, either 0 or 1 for each. And we are going to transform these into a display. And this is called a 7-segment display. Why? Because it has 7 LEDs, which will turn on or off in order to try to show a number. Okay. In this case, it's not just a number because this is an EX display. So if this is an hexadecimal display, it will show not only the numbers, but also the letters A, B, C, D, E, F. So now we are talking about hexadecimal numbering format, which has a total of 16 symbols from 0 to 9, and then from A to F. Okay, anyone has not had experience with hexadecimal numbers? Okay, so our goal is to say, as a function of the input variables, so for example, 0, 0, 0, 0 is a state which has the values of the variables all 0. And in that case, I want to have my function, and this function is not a function for everything. It's a function for the segment 1, and this segment 1 is here. So basically what I want to say is that when all these are 0, I'm trying to represent the number 0. And in the case of the number 0, the segment 1 should be on. Because why? Because I want to write, to paint that upper segment. So in this case, I would have to put there a 1. Não estou a mostrar. Depois mudei aqui, depois esqueci o record. É isto? So in the case, for example, of segment 2, when we are talking about the number 0 that we want to show, so when variables B0 through B3 are 0, 0, 0, 0, we want the segment 2, this one, also to be on in order to display a 0. So here it's going to be 1. For segment 7, for example, segment 7, in the case of the 0, this segment is supposed to be off. Okay? So because it's supposed to be off, in this case, I would put here an F. So now you can see that we don't have a single table of truth. We are going to have 7 tables of truth and 7 logical functions, 1 for each segment in the display. So each segment is going to be turned on or off as a function of the number that we want to show, or as a function of the state of the B0 through B3 variables. Okay, so this is not a good example, so I will not stop here. I will stop here. For example, as I told you before, from here you know that the segment 1 should be true for numbers 0, 2, for example, number 1, segment 1 is off, 3, and then 5, and then 6, and so on and so forth, okay? And from here we can derive a table of truth for the segment 1. With this table of truth for the segment 1, we use the kernel map, and then from the kernel map, we obtain the simplified logical function for segment 1. And then we do the same for segment 2, 3, 4, 5, 6, 7. That's why I'm trying to explain this in detail. That's what we are supposed to do in the practical assignment that starts this week until the next one. So we have here some examples. For example, for the segment 1, let's take a look at the segment 1. So now you remember that the segment 1 is the one on the top. So for the segment 1, when we have, when do we want the segment 1 to have, well, perhaps I will try to do something better. Okay. Now here, new one, EAI, what's the date today? Dash, okay. Dash, do dash. Okay. Oops. Then, okay. Now, let's try to work with segment 1. Okay, let's use the example of 1. It's as good as any other. So for segment 1, this is what it says, but let's try to do it from the start, okay? Now, we know that the segment 1 is this one, segment 1. The others I don't know by heart. I know that 7 is the one in the middle, but it doesn't matter. So that's segment 1. And now we have a table of truth for all the values, which I'm also going to copy paste, it's better. So again, I'm going here. And now I'm going back here and I copy this one. Okay. Insert a new image from the gallery. Okay, new one. Okay, so now we have here, oops, drop. The beginning of our table of truth. This is not the table of truth because we don't have inputs yet. We are working on it. So now for the segment 0, I think it's better like this. Okay, so now for the not segment 0, segment 1, we are talking about segment 1. Here we have the input values for each variable. Zero, 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 zero for B3 to B0 and blah, blah, blah. And we know that each of them will represent a decimal number, either 0, not decimal number. This is the symbol that we want to show. So in red on the left. So if we want to show a 0, for the 0, we will have to highlight these segments. So for the 0, we have here, where is the undo here? Undo. 1, 2, 1. We would have to show there a 1. Okay. For the 1, we would have to highlight this segment. So we don't have to show segment 1 on 0. For the 2, we would have to highlight these segments. Well, you know which segments you have to highlight. For the 2, this has to be 1. Then for the 3, we would have to do this. So that means also 1. The 4 does not have the top one highlighted. So for the 4, it has to be 0. For the 5, it has the top one highlighted, so it has to be 1. For the 6 is like this, no? So it doesn't have the top one highlighted. 7 is like this, so it has the top one highlighted. 8 also, then 9 also. A, I think is like this, so highlighted. B also highlighted clearly. C is like this, so highlighted. D is like this. These, I don't know. D, I think D is like this. So the top one is not highlighted. Okay. For E is this one, so it's clearly highlighted, the one on top. And finally, F, also 1. Okay. So this is what we are doing from the start for segment 1. And now finally we have the table of truth for segment 1. Table of truth is not just input values, also the output function that we want. So now we have to do the Carnot map, which should be this one here, but in any case, I'm going to try to do it from start, okay? So this one goes here, and I will try to do it from start. So we start from here. I will use the same sequence as they have, just to make sure that we will find the same table. So B1, B0. And here, B3, B2. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Okay. Now it's just a matter of going through the table and figuring out where to put the ones. Again, well, now take a look at the table. The table is filled with ones, right? There are much more ones than zeros. So it's much simpler that we find the zeros and put the zeros in the table, and then everything else is going to be ones. Okay, so I'm going to search for the zeros because it's easier. So first 0 is where B3, B2 is 0, 0, and then B1, B0 is 0, 1. So B3, B2 is 0, 0, then 1, 0, no, sorry, 0, 0, 0, 1, 0, 0, 0, 1, here. That's the 0, right? I will put this in black. I will need the colors for the group. So 0 here. Second one, this one. That's going to be 0, 1, 0, 0, 0, 1, 0, 0. This is it, right? Third one, 0, 1, 1, 0. So 0, 1 on top and then 1, 0 on the bottom. It's here. If I'm doing a mistake, please tell me. And finally, the last one is this one, 1, 1, 0, 1. 1, 1 is the third column. 0, 1 is here. So I think this is it, okay? So 4 zeros, I looked at where they should be in the table. Everything else are ones. Right? Let me see if the Carnot map is the same, just to see if I didn't make a mistake. So one. Actually, I think I did make a mistake. So this 0, supposedly this 0 is wrong. So this 0 was the last one, I think. So 1 1 0 1 1 1 0 1. Espera lá. Talvez, deixa-me verificar. Mas quantos zeros é que há aqui? 1, 2, 3, 4 só. Se o 6 estiver mal, quer dizer que o outro tem que estar mal ao contrário. So what Ricardo is saying is that probably I made a mistake putting the 1s and the 0s in the table of truth. Because perhaps I made a mistake with the 6. So first let's confirm the 6. So we are going to take a look at the PDF and try to confirm number 6. So number 6 has segment 1 on. So Ricardo was right. Let's put here number 6. It's not going to be a 0, it's going to be a 1. So by the way, 6 is going to be 0, 1, 1, 0, 0, 1, 1, 0. That's going to be a 1. So this 0 here goes to 1. Okay, Ricardo, obrigado. And then we have also this difference here. This guy here, which is a 1 that is in 1, 1. No, in 1, 0, 1, 1. 1, 0, 1, 1, it's B. So let's see how it writes B. Perhaps the B is like this. I don't know. Let's see how B is written. Capaz. Next over here. Yeah, so B is here. So for B, segment 1 is not on, right? So if segment 1 is not on, I also made a mistake here where I said it's going to be 1, but it's not. It's going to be false. So that means this 1 here will actually be a 0. And now, yes, we have exactly the same. So I didn't make a mistake building the Carnot map. I made a mistake building the table of truth. Okay, now it's correct, and it's exactly the same as the one on the bottom that was copied from the slides. Okay, now we have our Carnot map for the segment 1. Now we have to do some groups. So who can help me with the groups? Any ideas? Can anyone draw on top of my system? No. In Zoom, you have an option, annotate, and then you can draw. Ninguém consegue desenhar? I think it's not possible to annotate. In any case, what can we do in terms of grouping here? For example, the first group, I will perhaps start like Ricardo did before and say, okay, the first group is easy because it has to be this one, right? So that's the first group, no big deal. For a second group, what? This has a lot of groups, perhaps this one. Yeah, I think it's this one. Then, for a third group, we could do, for example, this. See? O amarelo? Ah, boa. So the yellow, this yellow group has only 2 of area, but Ricardo is saying that we could do it like this. And that would be a group of 4. Não percebi? Ok, mas então eu uso outra cor. So the yellow one is going to be orange. So this one, orange one. So a group of 4 with ones. And then we also have several ones which we must cover, and there is no easy solution for those. I will put them in let's say, blue or something. So for example, I think that we need to do this one like this. There is no way to put it. Also this one. Ah, boa. You are good with this, Ricardo. So this one like this, but in this case, we can do a group of 4. So it's better. Then, this one, yes, Ricardo, agora este não dá para simplificar, acho eu. Diga-me você com o seu olho clínico. Okay, now, another one. This one I think doesn't have any better solution, right? And then we are still missing this here, which also doesn't have a better solution. And for this one, we could do this, but again, that's not the best solution. We can do this. Okay. So a lot of groups, which makes, then you would have to go for each group, figure out the logical function. So in this case, I'm not going to do because we have a lot of groups, but I think it's there in the solutions. I should have tried to do this with a better number because segment 1 I think is one that is always on. Should have selected a more rare segment. Now, so from here we get the table of truth, the cardinal map, and then the same for all the segments. And then finally, we are going to, using all of these segments, using the cardinal maps, we are going to derive. So I'm going to derive the logical function so that you see what will happen. So we have a red one. Let's start with the red one. The red one is the group on the bottom, right? So our function is going to be, the group on the bottom is where B1, B0 is 1, 0. So B1 is always 1. B0 is always false. And all the others are irrelevant. Then I'm going to go to the purple one. So in the purple one, which is the 3rd and 4th row. So for the 3rd and 4th row, B1 is always 1, B0 changes. B1. And then in terms of columns, B2 is always 1 and B3 changes, so B2. Okay? Then let's go to the yellow one. For the yellow one, darker yellow perhaps. For the yellow one, we have the ones on the edges. So we can see that in terms of rows, we have the first and the last row. So the first and the last row is where B1 changes from 0 to 1, so it does not appear, and B0 is always 0. So B0 is always negative. Then in terms of columns, we have the first and the last column. We have B2 always negative and B3 changing. Okay. Okay, let's go to the CN. For the CN group, which is the one there in CN, we have the first and last row. So that's where B0 is 0. Then we have, in terms of columns, the 3rd and 4th column, and that's where B3 is 1. Are you following my reasoning? I hope so, because you are not asking anything. Okay, continuing. Then we have, I think, 3 more groups, the blue ones, okay? So I'm going to call it the blue 1, the blue 2, and the blue 3. So let's go to the blue 1. For the blue 1, what we have is the first and second row. That's where B1 is 0. And then we have the last column, and that's where B3 is 1 and B2 is 1. No, is 0, sorry. B3 is 1 and B2 is 0. Okay, so this is a smaller group, a group of size 2. That's why we have 3 literals. Now we go to the blue 2. For blue 2, we have, in terms of rows, B is not B0. And in terms of columns, not B3. É B0, como assim? No B0? Ah, tem razão. Ok, obrigado. And we have not B3 and B2. That's it, right? Obrigado. Finally, for group blue 3, we have, in terms of rows, we have B1. And in terms of columns, we have not B3. Right? And I think that's it. And this is the simplified version of the logical function. You don't have to try to simplify it anymore. This is already the most simplified you can get. So yeah, that's one of the things I love about Carnot maps. You don't have to wonder, oh, could I somehow simplify this any further? No, you cannot. If you did the groups as big as possible, the smallest number of groups, you don't have to simplify. So that's what you do, everything you do for a segment 1. Then, how do you implement this in your ladder? Well, you can go from here to a ladder function, which would be something like this. So in order to activate segment 1, let's say that we have a variable called segment 1. We have a red branch which has a contact that assesses if B1 is true, and one negated contact that checks if B0 is false. That's the red branch. Then we have a purple branch, which is an OR. So if this is an OR, you can either activate it there or with this. So this purple branch will be B1, B2. Then for the yellow branch, you have again an OR. So if because this is a plus, so if it's an OR, another branch where you test variables not B0, not B2, not B0, and not B2, and so on and so forth. I'm just going to do one more, the CN one. For the CN, you have not B0, B3. So not B0, B3, another possibility to activate S1. And okay, I do one more of the blue ones because that's with 3 variables. So for the first blue, not B1, B3, not B2, I'm going to do not B1, B3, not B2. And you also have to do blue 2 and also blue 3, right? And that's what you need to put in your TIA portal program. And you need to put this for the Siemens. You need to put this for segment 1 and then for segment 2 and so on and so forth. Any questions here? This is critical to do the program that we want. Any questions? No? Okay. So let me continue. Now, there is a second variation of the Cardinal maps, which is used when we have what are called irrelevant conditions, don't cares. So it may be that in your function, in your table of truth, you have an X and a Y, for example, and an F. And for 0, 0, you know that it must be 1. For 0, 1, you know that it must be 0. And for 1, 1, you say, oh, I really don't care. It can either be 0 or 1. I really don't care. It can be either 1 because it's not important. So it's also possible to handle the don't cares with the Cardinal maps. And here's how you can do it. So now we are going to talk about not an eggs display. So what's an eggs display? Is a display which must show numbers 0, 1, 2, blah, 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 until 9, and then A, B, blah, 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 until F, hexadecimal numbers, 16 algorithms. Now we are going to talk about a BCD display. So it can be that you are using a display also with 7 segments, like the one before, but where you are not interested in showing hexadecimal numbers, but instead decimal numbers. So you just want to show from 0 to 1 to 2 until 9. If that's the case, you are also going to need 4 input variables. Yes, A, B, C, and D. So you still need them. But there are some combinations of these 4 input variables that you don't really need, which are the ones on the bottom. So if you don't really need them, you just put there an X on the function. So that means you don't really care about this one. It can be either 0 or 1, I don't care, okay? By the way, do you know why we need 4 variables in order to encode these digits from 0 to 9? Because if we have 3 to the power of 2, if we use 3 variables, we would have 8. And we want to encode from 0 to 9, 10 algorithms. So we need a 4th variable in any case, okay? So these don't cares are going to be handled just like you would handle a 1 or a 0. It's whatever is better for simplifying the function. For example, this X here was used as a 1 because if you had a 1 there, you would be able to do a group of 4. And that would be better because you would have a larger group. So the X there was used as a 1. The X here, for example, this one here, this X here was used as a 0. Why? Because you don't need it to group the ones, therefore you consider it to be a 0, and you don't have to do an extra group, right? So that's how you go about simplifying Cardinal maps with don't cares. You use the X's either with as 0s as 1s or 1s in whatever way suits you better. Here's another example, so I'm not going to stop here. So this is the example for the BCD for 7 segments. In this case, we have don't cares here. Again, we are going to figure out for each segment, let's say S1, whenever we need to put either here 1 or 0 or blah, 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 we are going to fill this. And when we get to the other ones, to the A, F, blah, 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 we say X because we don't care. From here, we derive a Cardinal map, then we compute the groups, and from the groups, we compute the logical functions. Okay? So, oops, sorry. So it's exactly the same, but you have here the solution. My advice, don't look at the solution, try to do it yourself. So you have 2 classes. you can use this class to try to derive this by hand for the 7 segments. And then actually, I can even change the assignment. So the assignment was the practical assignment. Did anyone of you started it or not? Okay, so the practical assignment was to do a BCD display, right? But I want you to do an X display. Why is it? Because for the X display, you don't have this derived in your in the slides, okay? So try to do an X display if you can, instead of a BCD display. Okay, so these are the logical circuits. You know that from the logical function, you can go to the diagram of a logical circuit, but these are very, very complex. So we're not going to draw them. And now we have here some examples. I think I will do this example here. What time is it? Let me check the time. Yeah, we still have a lot of time. So I will do this example here. Or is there any volunteer? No, no volunteers. Okay. Sneezing is not saying yes, is it? Okay. Okay, so let's try to do this one. We already have a table of truth, so that's good. And it means that we can start creating the Carnot map. A, B, C, D. Right. And now, well, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. And now we start, so let's see. Now we have either zeros or ones or x's. And I think that the biggest, the ones that appear more often are the zeros. So I'm going to do the ones and the x's, okay? So let's start with this one. This one is in 0, 0, 0, 0, 1. Second, this is in 0, 0, 0, 1. 0, 0, 0, 1 here. Then this x is in 0, 0, 1, 1. 0, 0, 1, 1, x. Then this one is in 0, 1, 1, 0, 1, 1, 0, 1. Now an x in 0, 1, 1, 0, 0, 1, 1, 0. 1, 0, 0, 0, 1, 0, 0, 0, 1. 1, 0, 0, 1 for this x, 1, 0, 0, 1. 1, 0, 1, 0, 1, 0, 1, 0, it's a 1. And finally, 1, 1, 1, 0. And it's an x. Okay. So I think that's it. Let me just count. I have 1, 2, 3, 4, 5 ones. 1, 2, 3, 4, 5 ones, and 1, 2, 3, 4 x's. 1, 2, 3, 4. Okay, makes sense. Everything else is 0. Right? And now it's all about doing the maps. So for doing the maps, you know what we have to do? We have to ask Ricardo and he will tell us the maps, right? Now we can start. I will start with this simple one, then I can ask Ricardo. But the simple one is this one for start. For example, for grouping these, I could do it like this, but that would return a group of 1. Well, I can't do this because then I would include a 0, so I can't do that. But I can do this. Okay? That returns a group of 1. A group of 4 elements, which is better. What else now? Now I need to include, I need somehow to include this 1 here. So I have to, this one I think has no chance but to be like this. Okay. And now for the last one that is missing, I have to, well, actually here I think I have two alternatives. which are both equivalent. Either I do this, the green, or nothing else. It has to be the green, okay? Oh yeah, no, or I do this, the yellow. Okay, I could do also this. So group the one with the X. I think both are equivalent. They are the same. Let me choose the green just because I draw it first. Now we go from here to the table, to the logical function f equals. We start writing the. Diga. Nada. Sim. Mas consegue ser mais concreto? Você tem que fazer grupos para ficar com todos os uns cobertos por grupos. Okay? Todos os uns têm que estar cobertos. E depois você usa os x's. Como lhe dá mais jeito, você pode incluir os x's se lhe der mais jeito, para criar menos grupos e maiores, ou então pode não os usar. Está a falar de grupo? Você tem que colocar aqui, são todos eles. Portanto, você tem que pegar em todas estas. Portanto, você pode ir 0000 é 1, 0001 é 1, 0010 0010, escreva no 0. Você pode passar por todos e escrever. Isso nós também passar daqui para aqui. Você pode estar à vontade para perguntar, não sei mal. So I will try to explain in English again, but if you have problems, then I explain in Portuguese, okay? So the way of passing from the groups to the logical function terms. So what is a term? A term is, you know that these are going to be sums of products. So you know that you are going to have variables multiplying x times y or something like this. And then you're going to sum another multiplication, and then you sum another, okay? The number of terms, so a term is something like this. You know that you are going to have a red term, then followed by a blue term, and finally, a green term. Why? Why do you know that you are going to have this? Because you have three groups, right? Each group is going to be a term. That's clear. Now, for each term, what do you write here? So you have to take a look at the group and see, for example, for the red group, you can see that we are talking about the first and the last row, okay? So for A is this one and this one. So A is changing. A is 0 in the first row and 1 in the second, in the last, right? If it's changing, you don't write down. Okay. For B is going to be 0 here and 0 here. So it's consistently always false. So you write it down false. Sorry, the B in this example, it's B like this, false, right? Now you have to take a look at the other two variables, C and D. So we are going to talk now about the first and second column. And for the first column, let's talk about C. Not for the first column, let's talk about C. So C is 0 and 0. So in this group, C is always false. So C false. What do I put about D? So if you are understanding, how about D? D. We have D to be 0 and then 1. So if it changes, you don't put it. Make sense? You are not still off the hook. Let me just, I have to save because sometimes this goes crazy. I think I already have a lot of annotations. Okay. Okay, Mappers Carnot, recent files. Okay, now, Leonardo, né? Leonardo, if you understood, now you can tell me the blue part. So I'm going to ask you for help for the blue part. So again, the blue is going to be the first and second rows. So do you think A should be there? Positive or false? False, of course. A, not A, not A, right. B, no, because it's 0 and 1. So not B doesn't appear. How about C and D? What do you think should be there for the blue group? So we are, in terms of columns, we only have one column, this one, right? So in this one column, C is always false and D is always true. So C is always false and D is always true, right? The red group has 4 elements. So that's why we have 2 variables. The blue group has 2 elements, that's why we have 3 variables. So the bigger the group, the smaller the variables. So now tell me the green. Can you tell me the green? I will put it down here, the green, plus. So what is the green? Are you thinking first in terms of rows or columns? Linhas. Nós primeiro vamos sempre às linhas, portanto vamos ser consistentes. Vamos usar as linhas. Rows é linha. Portanto, vamos usar as linhas, não é? Linhas. Nesta linha, que é a linha do grupo verde, só temos, em termos do grupo verde, só temos a linha de baixo. Na linha de baixo, o que é que acontece ao A? A, B. A, not B, sorry. And then, how about the C and D? O C, verdade, vou confirmar. O C não, o C é 0 e depois 1, portanto não aparece. E o D é negativo, sempre aqui e ali também. Portanto, você está a dizer que é não D? Ok, eu já lhe pergunto outra vez, você já vai treinar mais. Então, no próximo você já faz. Ok, so that's how we would obtain the logical function, okay? In this example here, it says also to implement the logical circuits of the simplified functions. So let's try to implement the logical circuit of this function. F equals not B, not C, plus not A, not C, D, plus A, not B, not D. Okay, so how do we implement the logical function, the logical circuit of this? I don't know why. Está-me a chatear. Esta impressão foi horrível. Okay, we implement it like this. The result is F. Then we have the first one with an AND between B and C, right? Both negated. That's why you have those small spheres there. That's the first one. Sorry, not like this. We have here an OR, which goes there. Okay, now this one is going to be an AND between not A, not C, and D. So the first one is going to be the A. The second is the C, the not C. Sorry, not A, not C, and D. So now C, and finally the D. Okay, and then you just have to do the same, another branch. This of course goes there. You have to do another branch for the final term, which I don't have the space to do, so I will not do. Okay. Any questions about this exercise? I think this exercise was from an exam. Any questions? No? Right. Let's continue. Now, here we have exactly the same logic. We are using an X here, but this is just confusing because X is used for the don't care. So let's put here an F for the function. And this is without using don't cares, right? So let's try to do this also. Leonardo, go ahead. Essa questão da frente, I did not try to not help this, try to help. So okay. Wait a little, just a moment. Leonardo, you have 1, 2, 3, 4, 5 rows. So you just want 4 rows, right? São 4 linhas, 1, 2, 3, 4. Portanto, aqui vai estar, ou seja, o AB vai estar aqui, né? AB aqui. Se clicar no botãozinho, isso vai. Não. Deve seguir, passar não. Diga. Já falamos comigo, deixa-me. Depois voltamos assim. Se não estou a falar da primeira vez, escrever. Então, estou a dizer que eu fui escrever o AB aqui, não é? B, e depois o traço diagonal e o CD em cima. Ok, então agora tem que pôr aqui os valores das variáveis. O que é isto? Não consigo perceber isso. Isto é 1? Sério? 0,1, não é? Isto é 0,1? Ok, põe lá um bocadinho melhor. Ok, boa. Okay. Primeiro erro, os vizinhos. Não se esqueça que você não pode ter passagem de um lado para o outro sem os vizinhos mudarem apenas uma variável. Portanto, é sempre 0, 0, 0, 1, 1, 1, 0. O que eu disse logo no início, não. Portanto, aí tem que pôr mais vale pagar. Exato. Agora ali também. Não. Estava a dizer um aqui. E o 0, exatamente. Pronto, ok. É a mesma coisa nas colunas. Zero, 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 um e um zero. Ok, pronto. Então agora você olha para isto E tem que ver, portanto, das duas uma, quase todas as linhas e põe para lá o 1 e o 0. Ou descobre que os são mais frequentes que os 10 e põe só o 0. Portanto, aqui temos 1, 2, 3, 4, 5, 6, 7, 8 uns. Temos metade, metade. Portanto, pode fazer os uns e depois faz o. E depois tudo vai fazer. Então, primeiro onde é que tem que estar? Em que será que tem que estar? Isso onde é que está? Exatamente, vai aqui. Põe ali uma setinha, senão depois esquece. O primeiro ok. Depois, o segundo põe uma setinha no segundo Isso. É isso mesmo. Certo? Certo. 0, 0, isso é isso mesmo. 0, 0, 0, 0. Isso, continua. 0, 0, 0, 0, 0. Chama, você já não tinha. Eu já tinha passado por lá, não? Onde é que você está? Está neste aqui? Isto não é 0, 1, 0, 0, é 1, 0, 0, 0. Mas você está neste aqui? É 1, 0, 0. Isso. Ok, continuar. 1, 0, 1, 0. 1, 0. 1, 0. Onde é que está o 0, 0? 1, 0. Não, mas você não tem que olhar aqui, tem que olhar aqui. Né? Agora vai fazer qual? Este? Não. Você parte daqui. Ah, ok, desculpa, não tinha visto. É isso mesmo. Tá bom? 1, 0. 1, 0. Tá certo. 1, 0. Tá bom. É isso mesmo. 1, 0, 0. 1, 0, 0. 1, 1. Sim, está o número 0, 0. 0, isso. Isso mesmo. Só falta 1. 1, 0, 1. Não, 1, 0. 1, 0, 1. Não. 1, 0. Ah, não é 1, 0. Você está dizendo 1, 0, 1. Então, 1, 0. Onde é que está? 1, 0. 0, 1, 0. 1, 0. Cuidado com isto, se você se enganar a ler, ok, então temos aqui o mais bonito mapa de carga que eu depois vi. E agora, a ideia é passar, vamos fazer os grupos. Consegue pôr aí a cor de bem? Então, qual é o seu primeiro grupo? Passa assim aí, carrega aí, e escolhe o meu. Ok? Agora carrega fora. Então, qual é o primeiro grupo? Ora desenha, a ver se eu concordo. Mas então não põe a vermelho. Isso também pode pôr, mas então põe a preto ainda. Parece-me. Zero e tudo o resto. Ok? Então, grupos. Primeiro grupo 4. E agora, dá lá por outra cor, qualquer azul. Mais. E por último. Ok, então você tem 4 grupos. Um de 4, que é o primeiro, e 3 de 2. Alguém tem uma solução melhor? Ricardo, diga. Diga. Aqui não se não tem. Não, só que então já fez com o grupo azul. O grupo este grupo azul, o grupo este não. E a decisão também já. Ou seja, você tem que ter o grupo azul, estudei este grupo, e depois tem que ir buscar outros grupos, para ir buscar alguns possível. Você podia ter feito um mega grupo, pega nestes dois linhos e junta todos os linhos. Faz sentido? Então você pode ter um grupo de 4, não é? Então, estes dois juntam os dois. Ou seja, passa aqui, carrega uma vez, que é para tirar o último verde. Carrega outra vez, para sair deste. Outra vez para sair do azul. Isso, mais. Até sair os dois todos. Então faça logo o azul. O seu colega está a falar. Pode ser verde, pode. Não, mas não junto. Normalmente o que eu faço é por assim, ok, agora vai para o lado. Isso, e agora vamos ao outro lado. Pronto, 2 grupos, melhor que certo? E agora, função vermelha, escreve aí, escreve bola. Pode-se também. O fixe de engenharia é que você não tem que saber de cor. Então, aqui, para o vermelho, você tem, em termos de linhas, você tem o A e o B. Aqui, o A tem este e este. Está sempre? Não. O A está sempre de 0. Portanto, não há. O B, 0, 1, para B, portanto não aparece. E temos colunas. Ora bem, agora eu penso que é aqui. Para concluir. Isso, o B é 0 e 0, portanto, não ser. E quanto ao D? Porque é 0 e 1. B. Nós temos o A e o B. Depois eu não acredito, porque o governo passa. C. O mesmo que não processo. Por quê? Processo, você aqui, para pensa, você quando vai para as coisas, você diz assim, para lá, o A é verdadeiro e verdadeiro. O B é falso e verdadeiro. Você foi pensando no A, e pensa no B. Chega aqui e diz, o C é 10, falso. O que pensa no C e no D ao mesmo tempo? O C é o primeiro que aparece e o D é o segundo que aparece. Portanto, pensa só no C. Se for no C, Aqui, o quanto é que vale nesta coluna? Vale 0. E nesta aqui, quanto é que vale? Então o C não entra. E o D? Vamos só para o D. E aqui quanto é que vale? É o segundo, vale 0. Portanto, o que é que aparece? Não D. Ok. Faz sentido? Pronto, fixe. Mais alguma questão? Alguém tem dúvidas? Ok. Pronto, vamos lanchar e depois fazemos a parte prática, ok? Let's go for lunch. I don't know what time is it. Let me see. So it's 11, so at 11:25 or something we meet, okay? In 7-8 minutes. Então, o que eu não percebi? Diz-me outra vez. Sim. Porquê? 50. Fizeste bem, fizeste. Olha, falamos com a minha mãe para ela ver. Ela que venha ver. Ele falou contigo? Uhum. Ok. E fala com a Martinha, mas não tens o número da Martinha. Ela tem um pediatra, ou uma pediatra, não sei bem. Queres que eu te mande? Está bem, vou mandar então. Porque isso. Mas é assim, eu depois estive a pensar, Emma, pronto, eu tenho sempre medo dela ir para lá para as urgências. Ainda bem que tu vieste embora, porque realmente fizeste tu bem. É uma coisa. Olha, mas fizeste bem, mas o que eu quero dizer a febre dela não tem estado a piorar. Portanto, se fosse uma infecção, a febre não estava a ceder, e a verdade é que a febre tem estado a ceder. Ela hoje acordou com febre? Nem nada que se pareça? Quer dizer que está desde ontem, das 8 da noite, só com pé no ombro. Pronto, eu acho isto animador. De qualquer maneira, claro que sim, devemos vê-la, mas que ela deve ser vista por médico, acho que sim, mas realmente passar esse risco. Mas, isto é mesmo. Olha, adiante, não vale a pena. E vieste, estás em casa neste momento? Pronto, está bom. Vou-te mandar o número da Martim, está bem? Beijinho, até já, beijinho. Então, você tinha umas dúvidas, não é? Tinha chique, não é? O X é o binário. E essa pergunta, deixa-me ver, é Tomé, não é? Vou procurar aqui, só para me inteirar, que eu lembro-me da pergunta. Uhum. Certo. Se você quiser alterar o estado deles, quando carrego, onde é que você carrega? Pronto, exatamente. Então, o que está a acontecer é o seguinte. Isto que eu espero para explicar para toda a gente, porque isto é capaz de ser importante, ok? Então, Okay, so let's get started again. So first we start with a question from Tume, the colleague from there. He sent me an email and I said that we should discuss this. So let me try to do a scheme of what you are trying to do, right? Tume? So you have a variable, so in your PLC, you have your map tags, those are your variables. And these tags, these PLC tags have, for example, I0.0. That is going to be your memory address for variable SV00. Okay, that's it. And then in your HMI, what you did was something like this. So in the HMI, you created a very nice screen, and then you put here a button and the light, something like this, okay? This light would go green if SB00 was on. And this button would let you put on and off the button. That's it, more or less. Okay. But it's the same. So what you are trying to do is both to monitor SB00 and also to actuate on it, change its state. Now, what Tume said that was happening was something like this. Okay, so when he created these two buttons and the light, what he did was use the memory address, so create an internal variable from the HMI. Let's call it HMI SB00, which is connected. So there is a connection between SB00 in the PLC with HMI SV00 in the HMI. Okay, that's what happens when you create a tag which is connected to a PLC tag, as I told you last week. What he said was happening was something strange, which was the following. Let's say that the system starts and SV00 is turned off, so the light is off. And then you would click on this button, and by clicking on this button, the light will go on. But then after half a second or 1 second after, the light will go off again, will turn off without doing anything else. Any idea why this happens? Who can explain it? So again, what Tume was doing was clicking on this. When you would click on the button, SB00 would become true because the light would go on, would be turned on. But after 1 second or something like this, the light would go off again without him doing anything else. Why? The what, sorry? I don't think so. I think the button is like you click and it turns on. And then you have to click again to turn on. So it's not a button with condutor elástico. No, so it's switch, sim, switch. So the problem was not the button. In the button, no, the problem was not the button. Why do you think? The light was turned on when Tomé would press the button, but it would only stay on for half a second and then would turn off without him doing anything else. I told you the text. So SB00, memory address I0.0 in the PLC, and then you would have another tag in the HMI SB00, which was connected to SB00. These are the tags. Depends on what you want. Yeah, that's the reason why this is not working. I'm not sure. It can be a Q, yes, but it can also be an M, and it can also be an I. But there are consequences to each case. What happens in a PLC? The PLC has 3 stages. So it's a cycle in the PLC, which is happening always in loops. So it has 3 main stages. Read inputs, then execute code, apply. I never know if apply has 1 or 2 P's, outputs. So what happens in a PLC is that PLC works with variables that are connected to the real world electrically. Those are the inputs and the outputs. So first, the PLC reads the inputs, then executes the code, and then applies the outputs. For example, I0.0 is an input, so it will be turned on or off based on the electrical voltage that you have on that electrical input. So what's happening is exactly this. Because you selected this variable here in this input address, when you executed our code, you would press this to 1. That would put HMI SB00 to 1. That would turn on the lamp. Because this is on, it would put this SB00 to 1 also, right? That's executing your code. Then it will apply outputs, in this case nothing, and then it will go back and read the inputs, and it would say, reading the inputs, I noticed that the voltage in I0.0 is 0 volts. If it's 0 volts, SB00 is false. Or off, if you want, off. So now this is off. And because this is off, now this one is off. And because this one is off, the light goes out. So that's what happened is that you tried to set the value of an input, like he was saying. It doesn't make really a lot of sense that you try to change the state of an input, because inputs are meant to give you the state from the outside world. It's as if you pick up a camera and you want to photograph, but you say, I'm not going to photograph. I'm going to say which is the photograph, the picture that I'm going to take. So I decide. So if you have any electrical input, you shouldn't change the state of the variable for the electrical input. It should be given by the voltage that is there. What you could have done is change this, for example, to an M. So if you would use, I don't know, anything other than an I, M 10.0, let's say, this would not happen, because in that case, you would set the variable HMI SB00 to 1, then SB00 would be 1. That means the memory address 10.0 would be 1. It would apply outputs. It would read back the inputs, which do not change the internal variables, okay, the internal memory address. Você percebeu o que é que estava a acontecer, então? Então se percebeu, poderia-me ter poupado esta explicação toda, mas se você percebeu porque é que isto estava a acontecer. Não, mas repare, quando eu digo usa inputs, uma coisa é usar inputs, outra coisa é usar inputs, tipicamente só se usam para ler. Você aqui está a ler quando liga uma luz em função do input. O que não faz sentido, a única coisa que você fez que não faz sentido é escrever em cima do input, fazer um botão para mexer no input. Portanto, isto eu acho que não disse nos slides, para pôr um botão para mexer no input. Disse? Não. Se disse, não devia. É. Mas quer dizer, mas é um input elétrico, portanto, quando nós estamos a usar, ok, é um input elétrico. Se é um input elétrico, então, está aqui. Going back to English. So if you have, let's keep up with the I0.0. So what did I do in terms of experiment? I didn't create something like this. I think, I don't remember anymore, but this is what does not make sense. What makes sense for you to test this system, so what does the system do now? It turns on a light whenever the electrical input is on. So now what do? You can go to the PLC and turn on the electrical input in the switch, in the real switch, or you can turn on the PLC simulator and pretend that the electrical input is on. Okay, makes sense? Okay. Now for this this class and the next, the practical part, what we are going to do, let me share my screen. Is an assignment, a practical assignment where you have to do logical functions. So the idea is that you do first a BCD encoder or decoder, sorry, and let me share. So you want to have your HMI console with a symbol, with a drawing like this. And then you want to make sure that these lights turn on or off as a function of 4 variables, V0, V1, V2, and V3. Okay? Exactly. It's not recording. It should be, I think it is. No, it's recording, yeah. It's recording. So, what are you going to have to do? To compute the kernel maps. Well, for this, the kernel maps are already in the slides, but you have to pick up the kernel maps, compute the logical functions for each of these segments. This is segment 1, segment 7, all the others I don't know. And once you have the logical functions for each of these segments, that would be S1 equals V0, not V1, and blah, 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 for all of them, and then for all of them until S7 as well. Once you have this, you have to put this in your PLC program, and then this is done in the HMI. Okay? And based on the examples that I have already taught you in the previous classes, I think you can do this, no problem. So, you can see here the 7 segments. For example, if I want to, well, this is an example. And you have to, of course, compute the logical equations. And this is the specification of your assignment. So you are going to have to use the memory position I0.0 for SB00, I0.1 for SB01, and so on and so forth. So when you see this, the column on the left-hand side, referência elétrica, is supposed to be the name of the variable. And the memory address is where it says Sinal PLC, this one here. Okay, so this is the memory address, this is the name of the variable. And then you just have to derive all your logical functions, as I said, and create a program which will turn on variables, which are internal variables, M10.1, 10.2, blah, blah, blah. So each segment is going to be, HL is a symbol for an electrical for a lamp, sinalizador. So S1 will be HL01. And so on and so forth, okay? So your program should receive the Bs and should output a drawing of the algorithm that we want to show. If you do this very fast, because we have this class and the next, so if you can do it easily, there are people with different in different stages, some with more experience, some with less. So if you've done this, if you can do this very fast, that's good. You can do it, and then you create a new project where we want an X decoder. Okay, what's the difference between this? We don't want to show just the numbers from 0 to 9. We want to show from 0 to 9 and from A to F. So that should be a different program. And the biggest difficulty, the structure of the program should be the same. The biggest difficulty is that you have to derive the kernel maps by hand yourself. Okay. Any questions? Do you know how to start? Okay, so now it's important that you do groups. I don't know if you have already arranged the groups, but it's better to work in groups, I think. If you want to work alone, it's okay with me as well, but I think it's better in groups. So you can put together groups of 2 and start working, okay? This assignment is for this class and the next. So by the end of the next class, you should show this working. You should show it working to me. And that means that now you have about 1 hour and a half or something. Then you will have 2 more hours, but it's not going to be enough. So you should start today, right now. And then, as I told you, you can use the simulator, the PLC simulator, to work at home, okay? If you really need to come here, you can also talk to me, and I try to figure out a way for you to come here working, to work. But it's better to use the simulator. Okay, now finally I can shut up and let you work, and you can call me whenever you need, okay? After 3 weeks, I can shut up. Yes. falando em grupo, vocês ouvirem os grupos. I don't know if you want to give, I said it in English. If you want, you can arrange, try to talk to people to do a group. It's on you, okay?
Well, for the eggs, yes, but you can start with the VCD. Then it's from the VCD. Don't have the punches, but you can start immediately from the kind of mountain, the groups that you see there. You can put forward. Yeah, and this you can automatically write down the logical function. It's faster. Mas aqui não está que é. Tem que fazer isto, depois do mapa, e depois do oncológico.
We need to stop it.
No, Ricardo already solved it. Yeah, that's wrong.
Just one too much.
Yes, yes. At least one too much.
Já aprendi que eu sinto que começo a fazer as coisas mais depressa. Depois engano nem ao fato. Ou seja, é uma relação sistemática, metódica, e quando mais analisar, não é que você se engane. Porque depois o gajo está a ocupar 5 minutos, mas você se engana, vai ter que pôr lá. Isso nunca acontece. Ora, eu acho que não dói. Eu tenho que ver mais. O que é que se fala? Não tem que Vamos aí. Yes, always. What kind of computer is it? The 95 by the 7?
Then if you running it.
Yes, so you managed to do it. Like I told you.
I think it's small.
It should be, because everything's slow, but it's going to be slow anyway, so be patient. Just in Portugal, we always go take a coffee for everything. So we should do it. That will turn on. And they will come out these credits. That's one. Which will then be used to highlight the problem here. Which will show you the. Yes, I only do this. Short thing. That's just